on combinatorics and number theory, which is being organized by Sukumar sir, Stephen Bayer, Professor Bayer, and Lenjen Bag. Yeah. So it is a so um, so this talk is by you know Nilanjan Bag has been with us. You have all been acquainted with him, and you have been seeing him, I think, for about 1 or 2 years. Okay, so but younger students have seen you only for 1 year, and he's a very friendly person. I'm sure you all know, and also he's happy. He's an NBHM postdoc whose expertise is in um, number theory, and we'll come to know more today, specifically what areas of number theory he works in. But I think that you can always, if you are interested in this topic or related topics, you can always talk to him. Um, he can give you some friendly advice. You'll be more, you can be almost comfortable with, people who are around your age. So you can just talk to him while you are here. You can take benefit of his presence. So over to Niranjan. Thanks a lot.
First of all, thanks to our team very for organizing this, and thanks to Adhikesh and Stephen and everyone for organizing this event and giving me this opportunity to talk here. Surprisingly, this is the first seminar I'm giving here in these 2 years. I've taken classes, like small group lectures, but this is the first seminar I'm giving here. Yeah. So mainly some undergraduates and postgraduates are there, so I'll go very elementary. Although this analytic number theory talk, which needs more details and more refinement, but I'll go very basic, and I'll request all of you to ask me question whenever you want. Okay, so this is a work which is jointly done recently with Professor Stephen Bayer and his student Anu. So this is on multiple exponential sums, and we'll find some example application of this. How can this bound for exponential sum can be applicable to find solution of some quadratic congruences. Okay, so as there are many undergrads, I want to first define what is a basic exponential sum, why those are important, then I'll go to the much details. So the basic exponential sum are like this, like you want to find something in, so we'll be interested in Zn or Zp. So we'll be interested in such quantity, like, and these are exponential functions which is defined as ex e power 2 pi I x by Rn. In most of the cases, we will be interested in the case n equal to p, and we want to find some cancellations of these sums. First of all, you can see the trivial bound is n, right? There's n elements. We want to find cancellations and want to see how it can be applicable in analytic number theory approach. Okay. So there are many outside students also. For them, this is our campus, and I cannot show this is the mathematics department. Yeah. So let me first give the setup. Also, this photo is taken from Arkham page only. Okay. So what we'll do, we'll develop a method for evaluating some and estimating some general exponential sum. I'll define what is called general exponential sum with rational amplitude functions. Here I have taken only polynomials. Instead of taking polynomial, we want to take functions which is of the form f1 by f2, right? And naturally, we want to take f2 not equal to 0, right? And as an application, we want to find asymptotic formula for number of solutions of general quadratic congruences. In our case, we want to find it modulo p power n, right? And okay, I have to define what is the asymptotic formula also. So a typical asymptotic formula is of this kind. Suppose you want to find the order of p some prime, so this is of this form, some p power n and some error quantity. This is already defined this big O previous day. This is of some order which is less than n, right? And this C may sometimes depending upon some other epsilon also, but Usually this is some absolute constant. Okay. So in our case, what is general pure exponential sum? This we defined as some script s a p power n. This is summing over all those n tuples zb by p power m zp. These zp's are periodic integers. Don't worry, I'll define these things later. This is over e p power n fx. I have already told that we'll be mostly interested in taking the rational functions. So naturally we'll take f2 not equal to 0 modulo p. And what is this exponential sum? Same as here. So this is eq of x equal to e of 2 pi I x by q. And this is a generalization of the classical pure exponential sum, where we are taking, instead of this n tuple, we are taking only one, x from 1 to p power n instead of x1 to xn, right? And you can see there is a written in bracket without a twist. So twist means if you take such sums, sometimes we twist by some characters. So there is a character here, right? And those things I am not defining properly. So these are called Dirichlet characters over some polynomial I am taking. Any of those things are not used today. Okay. Now naturally, as we have said, what is the trivial bound here? This is p, right? This p power n. So m equal to 1 case, this is a famous work of Weil. One can show there exists cancellation of such sums. This can be bounded by some constant into square root of p. And this constant is basically the degree of this polynomial f modulo p, right? And if you extend it to rational functions, one can see the result of Bomberi. Like if you see the result of Bomberi, one can give the uniform upper bound of such sums in terms of the degree of the denominator and degree of the numerator. Now for mixed exponential sums, for example, one can see the work of Perelmutter, where we have the twist of by some characters like this. Okay. Now we are mostly interested in m greater or equal to 2 case. Just for the review, one can see the work of Chen, Professor Todd Kroken, Laxton, Professor Igor Sperlinski. This is the different Chen last sir has introduced. It's not the same Chen. And I am to just also tell about this famous bound. This is due to Hua. This bound is, one can write as less equal to some constant into p power m into 1 minus 1 by d. So d equal to 2 case, you will get the basically square root, right? And there are many other refinements later have been done towards this sum. But mostly what we are interested today, today we are interested in a method which is mostly used in the work of Todd Kroken and his collaborators like Zheng. We will be interested in a method called stationary phase type argument. What we want to do? We want to extend our Weil kind of sum to multiple variables. There we need this method called stationary phase type argument, which we will define later how it is going. And one can find the work of Kroken and Cheng to find such arguments for one dimensional case for mixed and pure exponential sum also. And later these are extended to rational functions. Okay, first let us fix few notations. For f, we are taking rational functions, which is of the form f1 by f2, where f1 and f2 are polynomial in the z x1 to xn. We are in the multivariable case, so naturally we will take the notion of gradient. So this is a vector, we are taking all the partials, like we have n variables, so you are taking the column vector del f del x1, del f del x2 to del f del xn at the points of x. So in the multivariable case, so if you have the consider Taylor polynomial, then we need the notion of Hessian also, right? So Hessian, as you all know, this is defined as if you take all the 2 degree partials in terms of all the variables. Suppose if you take del square f del x1 square and dot 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 del square f del xn square. Now I want to take what is the order of some rational functions. Before that, we want to know what is the order of some polynomial. If you know the order of f1 and order of f2, for such rational functions f1 by f2, the order is defined as the order of f1 minus order of f2. And order of Fi's are defined as the maximum of all those k's, such that if you take a polynomial like this, for example, suppose some 2x square, some 4x plus some 8, then what is the maximum order defined all the coefficients, that is 2, right? Order of this prime 2 is 1 here. So such like that, we take maximum of all those k's such that p power k divides all the coefficients of Fi. Fine, clear, right? Okay. Then I want to find what is critical points. First, let me fix some integer r, and this is uniform for the rest of the talk. R is the minimum of, if you take order of all the partial derivatives del f del x size, and then we define this critical point f, we denote it by Cf, as those n tuples from Zp such that p power minus r del fx is congruent to 0 modulo p. So why we are dividing by p power minus r? Basically we don't want it to be trivially 0 modulo p, right? And we now want to introduce this classical quadratic Gauss sum. This will be appearing in our result. This is GQN, this is denoted as GQN. This is equal to summation over from x from 1 to q eq xn square. Now one thing to mention that you can replace this square by any k to have the notion of generalized k Gauss sum also, and those are little critical quantity to evaluate sometimes. And you all know in the number 3 course, this is the standard Legendre symbol. If you have any a by p, this is equal to 1 whenever this a is square modulo p, otherwise this is minus 1. Okay, so we have at first some zp, right? So zp are of this form. We are taking all those elements which is of the form a naught plus a1p plus ai p power I plus dot dot, where ai's are running from 0 to p minus 1. But the quantity today we will be interested to evaluate is the same script as apn we have defined first, but we are fixing all those elements which is congruent to some alpha modulo p, right? Is this some clear? First, what we have taken at the beginning, we have taken a sum x from zp by p power m zp n tuple epm fx, but in this case we are taking all those x which is congruent to alpha modulo p. That's why we have taken this in script some alpha in this case, and the same we are taking only rational functions. And then this is one result which is recently proved with Professor Stephen Baer and his student Anup. We have what I proved, we can just simplify this sum a little bit. How? Suppose you are taking odd prime and FBA non-constant rational functions in n variable defined over some z, then we can simplify a little bit by reducing this zp by p power m a little bit to up to some r. That means we have the contributing term now for m minus r even case p power m into m plus r by 2, and this sum reduces to a little bit in terms of such critical points. Suppose how we have taken those critical points, we have fixed all those x such that p power minus r delta fx is congruent to 0 modulo p. So here we have same sums, but we want to lift the modulo p to some p power m minus r by 2 case. And for m minus r equal to odd, then we have the contributing part here p power m plus r minus 1 into n by 2 and this sum. One thing to notice, like this two in the above, there the modulus are same p minus p power m minus r by 2, but here it is little different. So directly lifting the solution to some power modulo p is not applicable. Here you have to devalue it a little bit more. So in the above, what we can do, we can just lift the solution depending upon the Hessian solution of this one to solution of p power modulo p power m minus r by 2. But for the odd case, we want a little bit of more evaluation because this two moduli are same different, right? This is r minus 1 and this is r plus 1. Okay, it's clear, right? Fine. Okay. Is it clear or? Okay. Yes. So then we are directly ready to directly evaluate what is the exactly the exponential sum. Now from the last sum you can have this is equal to this p power into this summation, again this p power into this summation over a equation like this, right? Then as the definition of critical point, suppose this critical point some alpha is not in the critical point, naturally this is equal to 0, right? Because there is no contributing alpha or contributing x, right? This straightforward. And now we are in the case whenever this is a critical point depending upon the Hessian. Now in the standard Hensel lifting for the n variable case, we know there is a lifting whenever this Hessian is not equal to 0 modulo p. Same like the dimension 1 case, whenever this derivative is not equal to 0, right? In the dimension higher dimension we are taking this Hessian. Then we can directly have this expression like this. So first one is quite trivial because this alpha star is basically the lifting of such solution to modulo p power m minus r by 2, and the second case as the modulo p power is little different, we need the little bit of evaluation, and here this is equal to some Legendre symbol into p power m plus r minus 1 into n by 2 e ppm e power e pm f alpha star into this Gauss sum, quadratic Gauss sum what you have defined. And this alpha star is the unique lifting of the solution to the congruence this p power minus r delta fx congruent to 0 modulo p to a solution to higher power of p, right? What we have in our case, whenever this m minus r is even and whenever this m minus r is odd. Yes. Now one thing to remark that where we have already evaluated the sum whenever this Hessian is not equal to 0. For Hessian equal to 0, this needs more refinement. Still you are unable to do it, but yeah, this is something which is subject to our future work. And for the same reason, here we don't have the lifting like using Hensel lifting. Okay. Now some application of this one, as we have told at the beginning, what application we'll have. So based on the last result, we will basically derive asymptotic formula like this to a number of solutions of some special quadratic congruence in several variable modulo some prime power, and quote unquote these some small boxes. I will tell what is small boxes. So first let me give some motivation behind it. Okay, so what is standard quadratic form looks like? This is we denoted by some q x1 to xn, summation goes from 1 to j I and j from 1 to n aij x I xj, where these aij's are running in integers. Then we are interested in detecting solutions of this congruence modulo p, and there is a lots of work behind it. So bit of history, for n equal to 3 case, that means in the 3 variable case, from the result of Sneijden, Slikkeloe and Smith, one can show that there exists non-zero solution in Z3 whenever this maximum of xi's are less equal to some constant into q power 2 by 3. This is the same big O argument here. And this was improved later. This was improved later by Heath Brown. He improved that this bound 2 by 3 can be improved to 5 by 8. So you can understand our motivation is to make it as small as possible. And one particular interest will be of this case whenever we are in the case q equal to p power m, and this was first considered by Hakimi, and with a special emphasis that the number of variables in that case is pretty large compared to m. And here we have a bit of introduction to the work which is happening here. So here first let me define what is diagonal quadratic form. It is same like, but we are having only summation ai xi square kind of term. So modulo p power m case, in a work from Professor Baer and Haldar, they have showed for n equal to 3 case, this is improved to 11 by 18, but they have some restriction. The restriction is that they have a strong condition that this GCD of product of xi to p, this is equal to 1. So in a result of Proken for general modulus q, one can say that there is a solution whenever we are in the critical range, this one, where this maximum of xi is less equal to some constant of q, square root of q. So in the above mentioned paper, they have refined the result. How? They also got the asymptotic formula for the number of solutions. So they got some asymptotic like this, right? And later in a work, Anup, he generalized to up to some 3 variable general quadratic forms. But what is our interest today? Our interest today is the general quadratic form for any variables. So first let us give the setup. We have in the, we want to find the number of solutions and we want to capture the solution in asymptotic formula. We want to find the solution of this q x1 to xn congruent to 0 modulo p for non-singular general quadratic forms, which we already defined. This is summation aij xi xj. But I want to find solution in some boxes, and we have already told this length of the intervals should be as small as possible, right? That means the an should be as small as possible. Okay. So before giving the main result, why this work is important? First, we developed this multivariable exponential sum, which is quite new to the literature. Those evaluation never existed, and then we are able to use that bound to find the number of solutions for general quadratic congruences, and this actually makes this method more elegant and quite simple. Okay, then we are ready to state what is the main result. So take any epsilon greater than 0, and if you fix the variable n greater or equal to 3, then if you take any Schwarzschild function and p be a odd prime, so roughly what is the Schwarzschild function? This is a C infinity function. Also this is a rapid decay. So what we call by rapid decay? This is going to 0 whenever x tends to infinity, but the rate at which is going to 0 is like faster than any inverse multiple of a x power. So roughly you can say like this, like this is going to 0, but this is very fast for any power, right? Okay. So then as m tends to infinity, we have this asymptotic formula. If you take all those n tuples in Zn such that these are not congruent to 0 element modulo p, then if you capture all the numbers in this quadratic congruence over this product of this Schwarz function at xi minus x0 I naught by n, this is asymptotic to some number. So asymptotic to means there we are giving the leading term. So in rough language, this is the leading term, right? Whenever this n is in this critical range, n greater or equal to p power half plus epsilon into m, where this small dp, this is equal to this cardinality of this below set by p power mn minus n. Where this cardinality, this is we are capturing all those xi's in Zn, where running all the xi's are running from 1 to p power n over this quadratic congruence modulo p power n, right? So is this statement clear? Okay. Yeah. So yes. Now I want to introduce to all of you why such results are important. So there is a famous problem in Diophantine approximation. It is called Oppenheim conjecture, nothing related to Oppenheimer. Okay. And these are basically representation of numbers by real quadratic forms in several variables. So in 1929, this was defined multiple times by Alexander Oppenheim, and later this conjectured property was further strengthened by Davenport and Oppenheim. What this conjecture is telling? It is saying that if you take any non-degenerate infinite quadratic form, indefinite quadratic form, okay, non-degenerate means this is discriminant is not equal to 0, indefinite means this q can take both sign, like there are x's such that this is greater than 0, there are x's such that this is less than 0. Okay. And whenever this n is greater or equal to 3, then this Q has a nice property that either it is proportional to a form with integer coefficients, or this Q at all z power n, this is dense in R. You run over all z power n element, these are basically dense, right? And you can take multiple example in your mind why this is so important. Proportional to form with integer coefficients. You can just calculate. You can find something which is not dense. Okay. So let me go to a bit of more history on this conjecture. Oh, okay. So this is, we are taking like this. Suppose some aij, xi, xj, and this is some real number here, and this cannot be done. Okay, suppose some, and these are z. This cannot be done. Suppose if you take 1 aij equal to root 2, right? Oh, this is not necessarily all the time. This is the same case. So in our case, we are basically looking at the periodic like analog of this one. That's why taking over integers or over Q. But for general quadratic form, we can define it on R also. So we are basically looking at the periodic analog of such results. That's why taking over Z or Z over Q. Yeah, this can be R also, like. Yeah. And this can be, suppose for example, if you take something like this, suppose some root 2, some x square plus, yeah, axy plus some b square. This cannot be always the first case. Okay, so let me proceed now. Okay, so the initial research towards this problem is vastly like around this, using the circle method, this famous Hardy-Little circle method. But as you all know, if you use circle method, then you have some restriction of variables on the number of variables. Then those are for large number of variables. But there is a definite work, and this is a famous work due to Margulis. He proved that this to be affirmative, this conjecture. But this uses this vast ergodic theory, which is beyond today's lecture scope, also beyond today's my knowledge also. It's too difficult for me to present even. And let us discuss a bit of this Mayer's theorem, from where this is basically motivated. So what is Mayer's theorem state? That if you take an indefinite quadratic integral quadratic form Q in n variable, where this n is greater or equal to 5, then it is represents non-trivially some 0. That means it is saying that there exists a non-zero vector x such that this Qx equal to 0. This is a famous Mayer's theorem, and this Oppenheim conjecture can be viewed as analog of this theorem. In our case, what I was saying, that it states that in this case the set of values of Q on integer vectors is dense subset of the real number, right? And there are many analog of the Oppenheim conjecture. One of the famous analog is this, which is due to Oppenheim and developer himself. He is saying that if you take some Q real in non-degenerate indefinite quadratic form in n variables, if you take n greater or equal to 3 and Q is not a multiple of a form with rational coefficients, then for any epsilon you can find some vector x such that this Qx is very small, right? Now you can see while finding 0 modulo p power n is important. Like that's why you are saying this is some periodic analog, our case. Just before finishing this part, I want to mention a bit that Margulis later remarked that in an implicit form this his work is equivalently occurred in some paper in 1955, in a paper of this Cassels, HPF, Swinton-Dyer in different language. Shortly after this Margulis paper's breakthrough, this proof was vastly simplified due to Margulis himself and our famous Indian mathematician H.G. Dani. So let us do a bit of comparison that so definitely our theorem has connections to this Oppenheim conjecture, and a quantitative version of the Oppenheim conjecture establishes that you can always find this x1 to xn such that this q at x1 to xn minus sigma is less than delta whenever you have this in the small box. We are in the p power m case, that's why we are saying, and also this m is going to infinity, that's why we are saying our result may be seen as the periodic version of this results. Fine. Okay. Okay, then let us give some easy proof to these things. Like first, I want to evaluate the basic exponential sum what I have taken. Now let us take how to define, how to simplify this exponential sum. So we have already fixed what is this r, right, in the top corner. Then let us divide into two cases. First, let us divide into whenever m minus r be even and n minus r is odd. When this is even, definitely this m minus r by 2 this is defined. Then let us break this all those x in the n tuple in such parts, like we can break it equal to x equal to p power m minus r by 2 z plus y, where this running z are running from zp by p power m plus r by 2 into zp in the n tuple, and we are taking the rest part, right. So if you just multiply p power m plus r by 2 and p power m minus r by 2, you are in the p power m. So this is right, this is fine, right. Then you can put this value of x here. If you just directly put it and write the range of this z and y, and as we are in our case we are taking x congruent to alpha modulo p, so here in our case it will be y congruent to alpha modulo p. Then we can just use this Taylor expansion up to 3 variables, up to third term. So in the multivariable case, in the Taylor expansion, we have the notion of gradient and the Hessian. That's why I've defined the notion of gradient and Hessian. Then if you put it, it will be simplified in these two parts, right? Because as in our definition, this is contributing some p power r. That means it will be total p power m, and that will be nullified because this is modulo p power m, right? Fine. Okay. Yes. So now, just a bit. Yes. Now what I want to do, we want to make this modulus and this modulus same, depending upon this one. That's what we have done. In the next part, we have subtracted the little contributing part p power m into r, summation over all those y's in the modulo p power m minus r by 2, where this y is congruent to alpha modulo p, and now we are in this just a simple exponential sum, and you know you have just the root of unity when this is 0 and this is not 0. When this is 0, whenever this other part p power minus r delta fy is not congruent to 0, right? If it is congruent to 0, this is giving the full sum, right? That's what we have done. So from there we have taken p power m minus r by 2 into n here outside, and this will survive whenever this is congruent to 0 modulo p. Is this part clear? This is just sum of root of unity. Fine. Okay, so this is the first case whenever m minus r is even, and same like m minus r is odd. So as it is odd, now we are taking 2 dividing m minus r minus 1. We take the same trick, basically the same, but here it will be a little different at the So if you do the same calculation, just will be like landing on the same case, but this two modulus is little different. And how this will work in the final theorem, I will show. Again, one can check that for L greater or equal to 3, this term will vanish. Okay. So trivially, our proposition 1, if you remember, that is whenever there is not a critical point, that is 0. That is true from the last expression. And what I do for whenever this is a critical point and Hessian is non-singular, we will use this Hensel lifting. For the first case, we can directly lift. That means we can directly grab some alpha star and put that alpha star in the exponential sum. That's all. But for the odd case, what we will do? We have to break it a little bit, because we cannot do the direct lifting because of this power of p's are different. So what we are doing here, we are taking some alpha star which is satisfying this congruence p power minus some delta fy congruent to 0 modulo p power m minus r plus 1 by 2, and put it here, adjusting the modulo in the sum. Then we can grab some u running over zp by p zp power n, and we can write this exponential sum as EPM f of this. Then naturally in this case we can again use this Taylor expansion. Then again we have this notion of gradient and Hessian, and one can easily see that the second term here will vanish again, right? But here we can do a little bit of calculation, because this is just a matrix. So we have this Hessian, this is a matrix, we can have a little bit of calculation to grab our Gauss sum now. What we will do, let us fix this. Okay, if you see there is a p power minus r into 2 into half into u transpose Hessian at f alpha star into u, we take the matrix p power minus r and into this Hessian and fix that as some a, and trivially this is a symmetric matrix. So we can grab some orthogonal matrix such that this P A P star P transpose, this is a diagonal matrix, right? And these are basically the eigenvalues. Then if you write this P like this row vectors R1 to Rn, then if you put everything together, then what is this U transpose AU? If you put the value of this A or this expression of this A, this is basically summation of lambda is Ri U square, right? And what is this P? This is basically invertible matrix. So this U goes to P is basically bijection. So you are shuffling the variables again. So if you put everything together, here basically this RIUs, R2Us, RNUs are basically shuffling U's all the variables. So this is again a complete sum, ZP by P into ZP. Now this is the standard Gauss sum, which we have already defined before. So this is the standard Gauss sum as we have defined before. This is like this, 1 to P E of some n x square, right? Oh, sorry. Then we can just break this exponential sum into product to capture the n quadratic Gauss sums. Now there is a result, like if you have a Gauss sum which is like this, and this is n is congruent to this co-prime to P, then it can be written as like this. If you define it by some Jn, that is exactly what I have done there, right? That's why in the last term we get this legendary symbol product of a lambda is into J1 Jp at 1 power n. So this is the same as this. Now if we put everything together, then we have this our expression for this exponential sum. Okay. Now briefly let us give the evaluation of this quadratic congruence. I'll give this is just a introduction in 2-3 lines. There is more refinements and more details to this proof, and it will needs again 1 hour. So what I've started with, we started with this quantity T. Now we use this some orthogonality property of characters to introduce some H here, like this. Then what we have done, we have divided this variable xi into 2 parts, xi equal to y into ki into p power m, and put everything together and use something called Poisson summation formula. This also needs some introduction. There is a notion of Fourier transformation, then we use this Poisson summation formula together, and roughly saying from here we will have this leading part. How? We just take ki's, all the ki's equal to 0. If we just put ki, all the ki equal to 0 here, this will give the term what we got in the beginning in the asymptotic formula. And we have to show the other part, this order is lesser than the contributing part. Okay, that's all for the talk. Yeah. Oh, it's submitted. Q of Rn? Q of Rn is a much bigger quantity, like where it is only sufficient to see the on Zn only. Then still it is dense on R. Yeah, sure. Yeah, so this we are taking much more elements. I don't know. Is there any number field version? I don't know. Also, I don't know about function field version also. Yeah. Yeah. Function field, yes? Okay. But I think a number theoretic proof will be a nice thing. Yeah. Yes, yeah. It's Margulis proof, but they simplified it later. Professor S.G. Dani also has worked on it. Yes. So, yeah, for circle method thing, there is a restriction of variables. The number of variables should be very large. So, usually with circle method, we need the variables to be large. Yeah. Of this quadratic form or this exponential sum? Yeah, there must be many, I think. Yeah. If studying averaging technique is, yeah, even this grabbing critical points and everything, there are like many maybe. We are working on a few. Like we are not now we want to focus on curves which are not homogeneous and all those things, like, but those themes are little critical and little complicated, so that may need some time. Yeah.
he's close to us, but not exactly with us. So his title, and by the way, I hope that you enjoyed the snacks. We got some tea and snacks. So it is an important part of a workshop. So the title of his talk is Extension of Maynard's work on small gaps between primes. Thank you for the introduction. I'd like to thank the organizers for giving me the.
And like Nilanjan, I mean, it's also surprisingly my first talk here. Though I have done my MSc here, I spent 3 more years as a postdoc, but it's my first talk here. Okay. So here is the title of my talk, an extension of Maynard's work on small gaps between primes. So most of the talk, it will be an elementary one, and just feel free to stop me anywhere you want. Okay. So before I move to the topic of small gaps between primes, let me introduce another one, primes in arithmetic progression. Okay. So let me define that. So suppose Q and A are two co-prime integers, and we define pi x q a to be the number of primes of x which satisfies the congruence, P congruent to A modulo Q. So in other words, pi x q a counts the number of primes up to x which are of the form A plus NQ. All right. There is the theorem, famous theorem due to Dirichlet. So he proved that pi x q a goes to infinity as x goes to infinity. What does that mean? So in other words, it tells us that every arithmetic progression of the form A plus NQ, where A and Q are co-prime, contains infinitely many primes. All right. Okay. Okay. For example, we can think about pi x. You can take Q to be 4, A to be 1 or 3, right? So we can think of pi x 4 1. We can think of pi x 4 3. What about pi x 4 2 and pi x 4 4? So how many primes are there in that arithmetic progression? So primes of the form 2 plus 4q. How many primes are there? So only one. And how many primes of the form 4q? 0, right? So this pi x 4 2 so this is 1 at least for x greater than or equals to 2, and this is 0. Okay. So what is the sum of this? I mean these 4. It is pi x, right? Because every integer can be written as either, I mean it is either of the form 10 congruent to 0, 1, 2, 3 or mod 4. 2, 3, 4 modulo 4, right? So this is pi x. Okay. Now here is the prime number theorem for arithmetic progression. It tells us that pi x q a is asymptotic to pi x over phi of q. In other words, we can say that the primes are equidistributed over arithmetic progression. All right, because from here you can see that pi x is, I mean this is asymptotic to pi x over phi of 4. This is also asymptotic to pi x over phi of 4. It is pi x by 2, pi x by 2. And this is 1, this is 0. We can ignore this finitely many primes. So, number of primes. So, in this arithmetic, in this asymptotic sense, number of primes of the form 4n plus 1 and number of primes of the form 4n plus 3 are same, right? So, you can say that the primes are equidistributed over arithmetic progressions, and this corresponds to this, whenever A and Q are co-prime, this we can call this a reduced residue classes modulo Q. Okay. So, we are interested in the error term of this asymptotic. What does it mean? The error means the difference between these two, left hand side and right hand side. So, we denote this by Ex cube. Okay. So, here is some results on the size of the error term. The first one is known as the Ziegel-Wolfes theorem. It tells us that the size of the error term is big O of x times log x to the power minus a for any positive a. So, what do you mean by this big O sign? So, suppose fx is a function and gx is another function. So, we can say that fx is big O of gx. It means that absolute value of fx is bounded by some constant times g of x. So, here is subscript a, big O a. It means this constant depends on this a, nothing else. Okay. Next result. So, under some strong assumptions, I am not going to into the details of GRH. I'm sorry. This holds for any positive a. A is arbitrary. Yeah, I'll come to that. So up to now, Q is fixed. So under some strong assumption, which is known as the generalized Riemann hypothesis, I'm not going into the details. So it implies that the size of the error term is of size, square root x times log x square. So you can see the improvement. Okay. And it is conjectured by Montgomery that for any positive epsilon, the error term is of size x to the half plus epsilon times q to the power minus half. Now forget all these, size of these error terms. Now in an asymptotic equation, when can we say that it is non-trivial? If the size of the error term is less than the size of the main term. So what is the size of the main term? Yes. Yes, here. No. So, yes, okay. So, the asymptotic is said to be non-trivial if the size of the error term is less than that of the main term, which is pi x over phi of q. So, roughly it is of size x by log x times phi of q. Yes.
The Q factor is not a problem.
Yes. Yes. Once I fix Q, this doesn't appear. Yes. Exactly. Yeah. Right. So as I mentioned that these three results, some known results, some conjecture, and some conditional result. So these are non-trivial. The first one is non-trivial if q is very small. Q can be up to log x to the any power of log x, right? Similarly, the second one is non-trivial if q is less than square root of x times some small thing. Yes. And the Montgomery's conjecture is non-trivial if q can go up to almost up to x. Okay. So here lies, so the range of q tells us that 2 is, 3 is stronger than 2, 4 is stronger than 3, right? But unfortunately 3 and 4 are, it is conditional and conjectures. They are not known. So far we know only 2. But we can improve this if we consider an average over the modulus. Okay. So what is that? Yes, LS chi. Yes. It's the classical Bomberi-Vinogradov theorem. So we can improve the Ziegel-Walfisz theorem on average over the modulus. What does that mean? So here is the statement of the theorem. So given any positive C, there exists another positive B depends on C, such that for q less than square root x times log x to the power minus b, we have this result. Now what is, just look into this equation number 5. So you consider the error term, take its absolute value. Now take the maximum of, take the maximum over all reduced residue classes. The maximum is taken over all A such that A is co-prime to Q. And then take the sum over Q. Okay. So we'll get big O of x times log x to the power minus c, which is non-trivial. Moreover, note that q can go up to square root x times some negative power of log x. Now recall what GRH implies. So GRH also implies that q can go up to square root of x roughly. So we can say that the Bomberi-Vinogradov theorem is of same strength as GRH. Okay. All right, so far. Okay. Now let me introduce another thing. It's called, oh, sorry. Oh. Yes. The level of distribution of primes. So it is defined to be, okay, first let me fix C. C is fixed. Okay. And in our case, you can consider C to be 2. Okay. That will be sufficient. So the level of distribution of primes is defined to be the quantity supremum of log q over log x, where the supremum is taken over all q, satisfying this equation 5. Okay. So you can see that q can go up to square root of x times log x to the power minus b. So we can say that level of distribution of primes is at least half. It is square root x times log x to the power minus b. So log q over log x. So it is at least, from Bomberi-Vinogradov theorem, we can say that the level of distribution of primes is at least half. Okay. Yes. Yes, but q always depends on x. Yes. Yes. For example, you can take for any given x, s is large enough. So q for any q less than square root x times log s to the power minus b, 5 volts. Okay. So the arbitrarily large. Yes. So roughly, I mean, so in practice, so q can be taken as power of some power of x. So we consider the maximum power we can take such that this equation 5 is valid. Okay. Yes. Yes. Okay, fine. And if you assume the Montgomery's conjecture, so you can see that level of distribution of primes is 1, right? But it is not known till then. Yes, yes, exactly. Sorry. Uh, no, no, it's not beating. It's of the same size because we are summing over q's. Okay. All right. So should I proceed? Okay. Okay. Now let's move on to the main topic of today's seminar, gaps between primes. Upper bound, okay, it can be proved that it cannot exceed 1. Okay, it can be proved. Yes. So gaps between primes is okay. Now P be the set of all primes, and all of us know that P is infinite. There is infinite many primes. At least we know at least one proof, the Euclid's proof, right? So let us write the primes in ascending order, P1, P2, P3, etc. And we define Dn to be the gaps between the nth and Pn plus n plus 1th prime, like this. So for example, if the sequence of primes is 2, 3, 5, 7, 11, 13. So the sequence of gaps is 1, 2, 2, 4, 2, and so on. Right. Okay. Now first observe that Dn is even for all n greater than 1. Only D1 is 1. Right. So all other Dn's are even. And here is an elementary result. For any positive G, there exists n natural number n such that Dn is bigger than G. So in other words, there exists arbitrarily long chain of composite numbers. And you know that, right? Yes. Okay. So high school algebra. Yeah. All right. So it is not bounded. The sequence Dn is not bounded. The prime number theorem implies that on average the size of Dn is of size log n. Okay, is the average size. It follows from the prime number theorem. Because the nth prime Pn is of size n log n. Using that, one can show that the average size of Dn is of log n. All right. Now, small gaps between primes. So what is our goal? So we have to study the lower limit of the sequence Dn, and we define it to be G of P, the limit infimum of Dn. So suppose it is finite. What does that mean? So if it is finite, then we can say that, say it is C, some real number C. You know that it should be even number, right? And so GP is C. What does that mean? It means there exist infinitely many pairs of primes which differs, infinitely many pairs of consecutive primes which differs by C, right? Okay. So here is the question: does GP exist finitely? And here is a famous conjecture. All of you must have heard it, the twin prime conjecture. So according to our definition, it predicts that G of P should be 2. However, we are far from this. Okay? And before 2014, it was unknown that GP is finite. Zhang first proved that G of P is finite, and here is the bound. Just forget about this bound. So beyond Zhang, it is known that GP is finite. Okay. So in the following year, Maynard improved this, and he proved that G of P is bounded by 600. And he received the Field Medal in 2022, Maynard. And both the result of Zhang and Maynard were based on another work due to Goldstone, Paynes and Ilrim. I'll come to that later. So it has been improved in the Polymath project that GP is bounded by 246. Just forget about these bounds. So concentrate on the fact that we want to study the finiteness of G of P. Okay. Yes. So we already mentioned the level of distribution of primes. Okay. And it is known that it is at least half, greater than or equals to half. Yes. So due to the works of Goldstone, Paynes and Ilrim, it is known that G of P is finite provided the level of distribution of primes is strictly greater than half. So they narrowly missed to prove that G of P is finite. But I should mention what they proved, that they proved that this one, limit infimum, the gaps Dn by log n is 0. Okay. They proved this one, but they failed to prove that limit infimum of Dn is finite. Okay. But still, it was a huge step towards in 2009, 2008 or 9. Yes. And Zhang proved an weakened version of the Bombard-Vinogradov theorem with level of distribution greater than half, and established that G of P is finite following the GPY method. Okay. So he proved that, so instead of the classical Bombard-Vinogradov theorem, an weakened version of Bombard-Vinogradov theorem will suffice. And he proved this version with level of distribution greater than half. While Maynard modified the GPY method and exhibited that the classical Bombard-Vinogradov theorem with level of distribution half is sufficient to prove that G of P is finite. Okay. This is the basic difference between these two works. Both are, highly pioneering works. All right. So let's come to our interest. So consider an infinite subset of primes. So let us write this P prime again in ascending orders, and you can guess that we have to consider this thing, G of P prime, where again it is defined to be the lower limit of the sequence of gaps between those primes in P prime. Okay, right? Now, if P prime is finite, does it ensure that G of P prime is finite? No. There exists an infinite subset of P prime of primes such that G of prime P prime is infinite. So it's a very easy exercise. Okay, just choose any P1 and P2. Yes. So take any two primes P1 and P2 such that P1 is less than P2. Now choose P2, P3 such that P3 minus P2 is bigger than P2 minus P1. Can choose P4 such that P4 minus P3 is bigger than the previous gap, and so on. Right? Following this, you can immediately see that G of P prime consisting the primes P1, P2, P3, etc. is infinite. Right? Okay. So comparing to the problem of finding G of P, it is even more difficult because P prime is a subset of P. So our goal is to find a sufficient condition on P prime such that it is finite. G of P prime is finite. Is it clear so far? All right. Yes. Yes. So let me state the result first. I'm not going to prove anything. Okay. So let P prime be such that there exists an arithmetic function beta. You know the definition of arithmetic function, right? Or you can consider this arithmetic function with domain the set of primes. That's also sufficient. So beta satisfies three conditions. I'll mention all these three. The first one is that beta of P less than equals to the characteristic function on P prime. Okay. So what do you mean by the characteristic function on P prime? So it takes value 1 if P lies inside P prime and 0 otherwise. Okay. So G of beta of P less than equals to this. Second is that what you just mentioned is that there exists some constants, positive constant C, such that for any sufficiently large n, we have this one. Okay. So if you replace this beta by the characteristic function, the left hand side is nothing but, and the left hand side divided by n by log n is roughly the density of the primes in P prime. Right? So just a minute. So from the first one, I mean equation number 6. So the characteristic function is an automatic choice for beta p, right? So it trivially satisfies 6. So if we just put beta to be the characteristic function here, so what does that mean? This I p prime of p p up to n. Okay, x, then it is x by log x plus some error term. Okay. So this is the size of pi x under prime number theorem. So if you divide this, the left hand side, so it counts the number of primes in p prime up to x. So this by this, so C should be the natural density of the primes, I mean of the set p prime. Okay. All right. So if the subset p prime has some positive density, then of course the equation number 7 is also satisfied by if we just replace beta by the characteristic function. Okay. However, the third one is difficult to prove in general for some p prime of particular interest. So what is that? Of course, as we can guess from our previous discussion, that the level of distribution is somewhere connected with the gaps between primes. So it says that okay, from 8 you can say that there exists some positive theta such that the level of distribution of p prime, I mean level of distribution for beta is at least theta. Okay. So these three conditions are required. So if beta, I mean there exists some beta satisfying these three conditions, then as I mentioned that the characteristic function I p prime, I mean to check equation number 7 is easier, but to check 8, equation number 8 for this candidate, it is really difficult. Okay. But maybe we can choose some suitable beta such that this happens. It's at least theta from this, some positive quantity. Okay. And then our conclusion is that g of p prime is finite. Now we have two constants, some positive constants c and theta, and g of p prime is explicit and it can be written in terms of c and theta. Okay. So as you get I mean as you can improve theta, or then of course c is fixed, so if you can improve theta, c will get better result for g prime, g of p prime. Okay. G of p prime is explicit and can be written in terms of theta and c. Yes, bigger theta will give a better, better result for g of p prime, better value. Yeah. But any positive theta and any positive c will give you that g of p prime is finite. Okay. So here comes an application. Yes, it has been proved. Yes. Yes. No, I mean, so sorry, n by. Actually, this holds for any n times any negative power of log n, but for our purpose, n, I mean -2 is sufficient. Okay. We don't require anything better. Okay, here is an application of so the Betti prime, it is defined like this. For any any alpha bigger than 1 and any beta belongs to R, then the primes of the form box of n alpha plus beta, is box means the greatest integer function here. Okay. For some n, so these primes are known as Betti primes. Our result can be applicable in case of Betti primes, but not for all alpha. I'll mention this. So usually one can take alpha to be irrational for Betti primes, but okay, we have a small assumption. We assume that alpha to be a finite type. I'll write down the definition, but you can ignore it. Just remember that for all quadratic irrational, I mean not all quadratic, all algebraic irrationals, alpha is of type 1. Okay, so you can think about all algebraic irrationals. Okay, so in that case, alpha is not only finite type, but it is of type 1. So the definition of type is here, but you can ignore it. It's a little more technical, but due to a theorem of Roth, it is known that all algebraic irrationals are of type 1. Moreover, due to a result of Khinchin, it is also known that almost all alphas are of type 1. So here I mention almost all in the sense of Lebesgue. Okay, irrationals. Yes. So as sir mentioned that so the advantage here of finite type is that we can have some nice rational approximation for those alphas, which will be crucial to prove the corresponding Bombay-Vinograd of type of inequality. Okay. No. Yeah. Yes. So under this assumption, one can verify that okay, it is easy but not immediate. One can verify that the indicator function I on those set of Betti primes satisfies all the requirements, all these conditions 6, 7, 8, and consequently we have G of P alpha beta is finite. Okay. Now I have roughly 8 minutes. I'll take 5 to 6 minutes more to move into something a little more technical. Yes, I'm sorry. Confusion.
Whatever you are going to say that whether it is infinite time, then your result is not going to be true or it is not possible to prove.
Okay, I mean it's not possible to prove. Okay, it's not possible to prove. As I mentioned that the finite type is required to prove that those alphas have some nice Diophantine approximation, rational approximation, which will be crucial to prove the Bombay-Vinograd type of inequality. Equation number 8, as I mentioned. Okay. And so some of you might know the holomorphic cast forms. So if be a holomorphic cast form of weight k and level 1. So this part is, I know this a little more technical, but that was my original purpose to study this kind of problem. I'll just mention the results. So it has some Fourier expansion like this, and these lambda fn's are known to be the normalized nth Fourier coefficient. And if f is a Hecke eigenform, so I don't define what is Hecke eigenform, then so under some assumption this function lambda fn is Hecke multiplicative. So by Hecke multiplicative I mean it is multiplicative and even stronger than multiplicative. Okay. So lambda fn is a, in that case for level 1, it's a real valued and multiplicative function. So it is known that due to the Delling's bound that for any prime p, lambda fp, the absolute value of lambda fp is bounded by 2. Okay. So it was originally conjectured by Ramanujan-Petersen conjecture. It tells us that lambda fp is bounded by 2. and it has been proved by Dellings. So now let us define a subset of primes of our interest. So we define P of PFI. So what is PFI? Is that take all those primes such that lambda FP belongs to I, where I is any subset of -2 to 2. Okay. Take any subset of I. We already know that for all prime P, lambda FP belongs to this interval. So take any subset of these, call it I, and for that we define PFI. So first fix F, then fix I, and define PFI like this. Okay. So the Sato-Tate conjecture, so though it is also, I mean, still now it is mentioned like Sato-Tate conjecture, but it is now a theorem. Okay. So it implies that if I is of positive Lebesgue measure, then, so what is I? I is a subset of -2 to 2. Okay. So if it is of positive Lebesgue measure, then P of PFI contains infinitely many primes. So we have an infinite subset of primes. Okay. And we are going to study G of PFI. Okay. Yes. So the first result in this direction is that Wong proved that G of all those primes P such that lambda FP not equals to 0. For this it is finite. So what is the I considered here? So I is here this -2 to 0 union 0. Okay. So then this, yes. So it is finite, but we are, I mean, the problem becomes even more difficult if we consider, I mean, if we make I to be smaller. So is it clear? So as I becomes smaller, the problem becomes more difficult. Okay. So this is the only result known in this direction. So here is our result of sorry. Okay, just consider the whole page here. So the class of subsets we are considering here is of this form. These are some subsets of, I mean, some basic subsets. Yes. So first we consider intervals of this form -alpha to alpha, where alpha should be, I mean, bigger than 1. Okay. The next thing is another type of interval. So -2 to -alpha or alpha to 2. So that means mod of alpha here is should be less than 1, when alpha is strictly less than 1. And intervals of this form -2 to alpha for alpha lying here, and the final one alpha to 2, where for all alpha lying in -2 to -half. So just consider the first one. Okay. So this is 0. So we consider, sorry, this is alpha, not infinity. So intervals of this form, but we cannot take -1 to 1. Okay, there is some limitations. So these, I mean, in all those cases, we have some limitations. These limitations comes because of the first condition in our result, that we need to produce a beta such that beta of p is bigger than the corresponding characteristic function. So we can produce certain beta for only for those alpha. Okay, so that is the limitation of our result. But if I be any of this type of intervals or subsets of I, subsets of -2 to 2, then G of PFI is finite. That we can prove. Okay. So of course, from this it is obvious that what is still open is that for to prove G of PFI is finite, whenever lambda of I, this is the Lebesgue measure, lambda of I is positive. Okay. But that requires a Bomberi-Vinogradov type of result for PFI, which is not known unconditionally. Okay. So that's all. Thank you. Yes. Which one? Yes. Yes, one expects, but it is not known. Yes. And I mean, if that is known, then the problem boils down to, that G, we can prove this for any type of I, any subset I of -2 to 2 with positive Lebesgue measure. For this we can. For BT primes, actually, if it is a finite type, then we can prove the corresponding, yes, the Bomberi-Vinogradov result. And following the original argument of Bomberi-Vinogradov. Yes. Positive. Oh, okay, the first line. Okay. So the Sato-Tate conjecture tells us that if I is a positive Lebesgue measure, then P of PFI contains a positive proportion of primes. So in other words, that, okay, that is the statement of Sato-Tate conjecture, is that consider number of primes P up to X and P belongs to this PFI. Okay. Now consider all primes up to X. So number of primes up to X, that is pi X. So as X goes to infinity, this is some positive constant depending on I as X goes to infinity. So from this you can relate to the fact that these are PFIs are of positive proportion. Yes, sorry. Yes, so now the limit exactly, exists. Yes. C is positive. So if I is of positive Lebesgue measure, then Ci is positive. So roughly we can say that asymptotically, so these primes are of positive proportion. They have some positive density. Yes, that is possible. We can construct something like this. Okay, so for example, just among all those primes, such that so it is proved that G of P Fi is less than or equal to 246. Now consider only those primes for which the gaps is less than or equal to 246. So these are of, okay, so sorry, you are considering only in this case, PFI, right? Okay, no. So no, yes, in that case, saturate, I mean, this is 0. So if you look into the second result, of our this, for require that C to be positive. So at least we can say that so our result fails to prove this, but that might be true. Thank you.
Now, is there which are there if you are interested in PhD?
Can you send me your slide?
Yes. Okay.
I'll refer a person and I'll give his number and this thing, or I'll
Okay.
ask him to contact you.
Sure.
Otherwise, it is very difficult now.
Yeah.
Very good.
Thank you.
General case also in that. Hardware examples also. If it works for I, it works for minus I. It is great effect always.
This works for, yes.
That can be
Because I mean the Lebesgue measures are same in this case.
break measures are same.
So then this proportion is also, I mean, it is same in both the cases.
So finally we'll get finite mass.
No, sorry. If we replace I by minus I.
Suppose for I it is finite, whether it is minus I also. GPA, whether it will be finite.
Yes. Because this, I mean, all we require is that the density type of result. So if it is holds for I, and then it should hold for minus I.
It's not clear for me. Because all the examples you gave, it was perfectly working like
Exactly. Yes.
So how is it at irration now? The full
Yes. Then
should happen.
yes, but yes, because and that is beyond the area of, I mean, scope of this result, but
Telling because it will be interesting if it is not a trivial result. It's true for I, whether it is true for minus. You can expect, but it's really
no, but for okay.
Some of you please come to the stage.
Just সেটা অফ করে কি করে